So last time we came to relativity, we discussed the idea that time must run slower. Clocks must be slower inside of spaceships. So moving things close to the speed of light. Again, if you're not going anywhere near the speed of light, you'll never notice this. But when I get in a car and go up to incline, I tell you I'm going to meet you at 11 o'clock, our watch is set to the 11th decimal place of a second. We got perfect watches. When we arrive there, my watch is going to read 1/11th, 1 times 10 to the negative 11th seconds less than your clock. And we stare and go, what's wrong with our clocks? The answer is nothing. I just lived 1/10 times 10 to the negative 11 seconds less than you did on my way up there. So my clock only had 1 times 10 to the negative 11 seconds less worth of time runoff. Again, that doesn't matter, right? We're never going to notice that on an everyday basis. But the weirdness keeps continuing because relativity has some more surprises for us. As a direct idea, let's talk about, we've got a train, we've got a spaceship. Let's do our spaceship again. Spaceship. I'm aliens. I'm putting them on a chocolate chip apparently. Okay, whatever. Oh man, that's so bad. We have to fix it. All right, whatever. Okay, come on. There, we can do it. Okay, so my little rocket ship. He's going very close to the speed of light, and he's going to shoot a beam of light. Boop, boop. He's going to whip around and get right back to the spot here. And that light's going to drift off here. It's going to hit some sort of mirror, and it's going to come sailing back, and he's going to hit him there. Meanwhile, I'm going to have an observer standing right here with a stopwatch. He's got a little stopwatch right here. He's not going to move around at all, and he's going to watch what's happening. Now, again, there's something to this that I'm sliding past. I don't want to talk about in great detail. If you want to argue about general relativity, it's just easier to see it this way. But so this light takes off, flies to there, hits that little light mirror, and comes flying back. We know the speed of light is 3 times 10 to the 8th meters per second, so you might be under the misapprehension that it makes perfect sense to say this is 3 times 10 to the 8th meters, that it would take, according to this guy here, it's going to take 1 second there, 1 second back, or 2 seconds. That makes perfect sense, does it not? And nothing wrong with that. Except we just discovered that this guy's clock is running slower. Uh-oh. Since he's traveling near the speed of light, he's going to read, maybe it takes 4 seconds. Now we got a problem on our hand because one thing that can't change is the speed of light. You always have to write your own reference frame. The speed of light is always the same no matter where you are. Therefore, that can't be wrong. That can't be wrong. So what's wrong? Oh, well, clearly, this guy here, according to people in the rocket ship, this guy here has no idea what he's talking about when he says it's 3 times 10 to the 8 meters away. If it takes 4 seconds to get here, if it takes, oh, I'm totally wrong. His clock is running slower, so it takes 1 second. I'm about to have a really bad situation. Okay, so back up. When your moving clocks run slower, so this should say 1 second, right? So he looks and says, wait a second. There's no way. If it takes 1 second to get here, the total trip should have been 3 times 10 to the 8th meters, right? So actually, the mirror has to be only 1.5 times 10 to the 8th meters, okay? Because it took 1 second to get there, 1.5 times 10 to the 8th meters, and then 1.5 times 10 to the 8th meters back, and that's how I measured 1 second, because the speed of light can't be wrong, my clock can't be wrong, I've right to my own reference frame, so therefore, you must be measuring distance wrong, Mr. Guy standing on Earth. Mr. Guy standing on Earth says, I'm measuring it right, you're measuring it wrong. So what's happening here? Well, it turns out moving meter sticks also shrink. What? Moving meter sticks also shrink. Let me give you an example for your eyeballs. All right, so what happens is this. The car's normal length hits the gas pedal, goes faster and faster, gets faster and faster, it appears to shrink, but only in the direction it's going. The cars keep the same height, it just gets shrinkier and shrinkier and shrinkier. You're like, oh God, the poor people inside. But the people have a right to their reference frame. From their perspective, the car isn't shrinking at all. Not even a little bit. From the people inside the spectrum, steering wheel still where it was, the wheels are still where they are. I don't know what you're talking about. My life is not shrinking. The person themselves would shrink in the one dimension that they're traveling in. So it gets skinnier and skinnier nose to rear, but it would not get skinnier. It's still be equally wide car, equally tall car. It's just skinnier in that direction as traveling in, because that's the only way to make relativity work. And then here's up being your formula, the same sort of thing, where you have 1 minus v squared over c squared. Makes perfect sense because it's related to the time, as we just derived it from looking at time, right? If the time must be longer, then the length of the car must be shorter. By moving cars must in fact be shorter in order for the speed of light to be maintained. Okay? Now, here's the first bit of the rabbit hole. You have a right to your own reference frame. And this is going to bother you, so take a deep breath because it's about to get bad. If you're sitting in the car and you look out the window traveling at near the speed of light, what does the city look like to you? I'm going to pause here a moment. If I write to my reference frame, the city's moving, right? So the city's got to be getting... So in what must seem like an apparent contradiction to you, the city must in fact be shrinking, right? I write to my reference frame, the buildings are flying past me near the speed of light. They're the ones getting squeezed. They are no longer the same width. They might be the same height. They might be the same in the other direction, but the direction I'm traveling in, they're going to shrink in. And I asked a question last time that was the leading question. That is, if you're traveling at the speed of light, what does it look like if you're instantaneously, your time stops, so they instantaneously go wherever you're going to go? It means that the universe must shrink to infinitesimally skinny. It shrinks and shrinks and shrinks until it becomes so small, you can instantly travel across it from your perspective. Yeah, can't go fast at the speed of light because the whole universe shrinks to a thin paste when you do that. Yeah. Which, by the way, has some nice ramifications in terms of space travel. You want to get to the next nearest star system, it takes 10,000 years. Oh, Lord, I don't want to do that. That's a really long trip. I'm not going to make it. Well, here's a trick around that. Go really fast. Go really fast. Go near the speed of light. If you go near the speed of light, not going to take you much time at all because it's not very far away. But, yeah, it's not very far away. You'll get there in a heartbeat. If you go fast enough. Oh, that's not good. Your clock will be slow. Not much time comes off the clock, and you get there fairly quickly. Spend some time on the planet, come flying back, no trouble at all. From your perspective, it would be a fairly easy trip if you could figure out a way to get a rocket ship to the speed of light fairly quickly, which is something well beyond our technology at the moment. I will say this, though. People watching your trip are going to say your clock's been running slow. Our clock's been running normal speed, so yeah, you get back. We've run a lot of time off the clock. More on that later. Next up on our list is the joy that is mass. So imagine for a moment you have an Olympic raft racing class, right? And you're trying to go for the gold. So you're allowed to put people in the waters, right? So you get some really great swimmer back here, and he normally swims by himself. He swims at something like 5 meters per second. And you put him behind a raft, well, he's going to push the raft at, say, 2 meters per second. Now, if you want to make the situation better, what are you going to do? You take another Olympic swimmer that can swim at 5 meters per second, harness him in. Now the raft's going, say, 3 meters per second, right? I'm doing better. And put another one on there, and you might get to maybe even 4 meters per second, although that's a stretch. And then you harness them together, put a stick behind them, put another swimmer back here, and start pushing farther. And now you get to 4.5, 4.7, 4.9. What's the limit of this, though? What has to be the limit? The limit has to be the 5 meters per second. They're not going to swim faster because more people are pushing the raft. They can only swim 5 meters per second. So the best they can do is 5 meters per second. Now, we just discussed how you can't go fast at the speed of light. If you can't go fast at the speed of light, that means if I push something, I can't push it to the speed of light because I can't reach the speed that is my maximum speed. So since the fastest thing is light, we can't push anything faster than the speed of light. Now, here's the converse from a physics point of view. Now the converse, what that means sort of thing. We know that when trying to push something, how hard it is to push something is expressed in this cute little expression right here. Whereas this thing that we call mass is determined, tells us how hard it is to push something. Well, as you get closer to the speed of light, adding the same number of swimmers, one more swimmer, doesn't do much. So what must be going up as we get closer to the speed of light? Oh yeah, your mass is going up. Oh dear gosh. And it's the same sort of formula you end up with. M equals m naught square root of 1 minus v squared over c squared. But more important for our conversation, okay, the mass goes up the closer you get to the speed of light, which means you can't go fast as the speed of light, because what happens when c gets to v squared gets to c squared? 1 minus 1 is 0. Square root of 0 is 0. My mass becomes infinite. Now notice it doesn't affect the mass of the guy sitting in a spaceship. Again, the guy in a spaceship, I mean, he may be fat. He may be 100 kilograms. Let's make him 100 kilograms. He's walking around. He's still 100 kilograms. He doesn't know he's going to the speed of light. But a guy watching the planet in front, if you're going fast enough, start screaming, because if you're going fast enough, you can get infinite. At the speed of light, you have infinite mass. That guy is not just fat; he's humongous. And so, as you apply more energy to make it go faster, some of the energy gets stored in mass, and it becomes how hard it is to push something. It becomes harder and harder to push it as you get closer and closer to the speed of light. And so we look at that and say, aha, yet another reason why you can't go fast at the speed of light. Now, this has been observed in supercolliders. As we make particles go around, they get heavier, they get more massive. As we try to make them go around and around these speed things, right? We put magnets and stuff, we kick them with things. Why can't we go fast at the speed of light? We can keep kicking it every time it comes around. Every time we kick it, it does less good. It gets a little close to the speed of light, but it's never going to get across it, because you're just adding swimmers to your raft race. You might get closer to 5 meters per second, but you're not going to get to 5 meters per second, because it would be better to cut the raft loose and let everybody swim by themselves, right? So guarantee if you push something, it can't push it faster than the speed of light. So therefore, every time it comes around the loop, you hit it with a laser, make it go faster, fine, but it goes a little bit closer to the speed of light. So there's one other implication in this cute little mass argument, and that is this thing that you'll see when people talk about physics all the time, and we haven't talked about it at all. 2 years of physics, we've never talked about this cute little formula. And the formula basically is, this is mass in kilograms, this is speed of light, 3 times 10 to the 8th, and this over here is energy. It's the energy if you destroy mass. More specifically, it's actually the energy the thing is storing. As the thing sucks up kinetic energy, it's not going any faster, right? It's 1/2 mv squared, but your v is not going up like it should. So some of it's getting stored here in your kinetic energy. And when you slow down, it bleeds that back out. As the mass disappears, you get that energy back. As you slow down, that energy has to come back. It's conserved. So as you lose that mass, you get this energy back. Now, it's freakier than that, because it turns out mass has always been the storage point for energy. More on that later. All right, so basically bottom line is, when you are traveling a spaceship, you don't notice any of these effects, but your meter stick is going to shrink according to the guy standing on a planet watching you. Your mass is going to get bigger the closer you are to the speed of light. Both these things happen. It's legit, been measured, can be tested, and has been tested. All right? All right, so I'm going to put you to the end of this one, and I'm going to post a question for you to deal with.